Alright, so we'll be talking about resting membrane potential and how it's established in the cell. And so if we have our cell, and what establishes the membrane potential is basically the distribution and flow of ions in and out of the cell. And so we have, in the cell, we have potassium, sodium, we have proteins that make up a negative charge, chloride that makes up a negative charge. We have calcium in the smoothie R. But mainly the two we're going to be talking about is sodium and potassium. And we have lots of sodium outside the cell. And this thing's right in the way. I don't know why I drew it right in that way. Anyway, and then less sodium inside the cell. We also have lots of potassium inside the cell, but less outside the cell. And so how the resting membrane potential of a neuron is negative 70 millivolts. And so how we get this, first we have these sodium potassium pumps, and they're all across the membrane. And it uses ATP to pump 3 sodiums out of the cell. And then it uses, ATP, it uses it takes 2 potassiums and pumps them into the cell. And so this sets up our chemical gradient where there's more potassium inside the cell than out. And as well, there's more sodium outside the cell than inside the cell. And so this sets up that gradient, which is really important. Excuse me. We have also leak channels, potassium leak channels. The cell is pretty much, for our purposes, impermeable to sodium. And so we have these leak channels where potassium will continue to just leak out, again, all across this membrane. And as potassium leaks out, it causes a separation of charges. And so positive charges will be leaving the cell, leaving negative charges inside the cell, making the membrane more negative. Let's see. We'll talk about the Nernst in a bit. Something that happens though, so we're pumping 2 potassiums in, but then potassium's just leaking out. And you would think it would just continue to leak out until we don't have a very good gradient. But what happens to create an equilibrium is because all these positive charges are leaking out and building up, as well as the pumping sodium positive charges out, we have all kinds of positive charges that set up an electrogradient and actually it repels these potassium wanting to come out, and it pushes them back in. And so it slows the rate of the potassium leaving the cell through leak channels. And so we reach an equilibrium because the rate of potassiums coming in eventually is about equal with the potassiums leaving. And so we can maintain voltage. In the cell, like I said, we have a negative 70 millivolts. That's our resting membrane potential. And so the cell at rest, that's its charge in the membrane. And how we get that is through what's called the Goldman's equation. It's a long equation that takes up into account all the ions passing in and out of the cell, as well as the cell's permeability of those ions. And so it's a long equation, but we can get this negative 70. But we can figure out if the cell is totally permeable to 1 ion, and in a fake scenario, this doesn't happen in a real cell, but we can figure out the charge the cell membrane would be if there was just potassium, or the cell membrane was just permeable to potassium. And that's through the Nernst equation. Yeah, you can still see that. Which is E of x meaning the ion we're using, so let's use potassium, is equal to negative 61.5 over Z, which is the charge of that ion you're using. So in potassium's case, we're using +1, multiplied by the log of the concentration of the ion in the cell and the concentration of the ion out of the cell. And so I don't know real numbers, what happens in a real cell, but I think an example used in class was, so we'd have Z is +1. In the cell would be 150, out would be 10. Not sure if that's accurate, it's what I can remember. And we get like a -90. And so E of X of potassium is around -90. It could be -95. I don't remember exactly, but for example's sake, this will work. And so for sodium, we get a lot less in and more out. And so an example used in class for sodium was like approximately +55. Again, if it was just sodium. And so what we can figure out from that is, because the cell favors this -70, so actually favors more potassium inside the cell. But we can figure out the driving force of each ion. For example, in sodium, the driving force of how badly it wants to enter the cell. Potassium, how bad it wants to leave, through this equation. So driving force equal to, yeah, you can see that, is equal to the voltage of the membrane minus E of X of whatever ion you're wanting to use. And so voltage of the membrane, we know is -70, minus, if we use potassium, -90. And so that would be about +20. So that's how bad it wants to leave the cell. Whereas sodium would be -70 minus +55, which would equal, what is that, 125? Let's see, minus 55. Yeah, so -125. And so you can see that this has a lot greater driving, sodium has a lot greater driving force that wants to enter the cell than potassium does. And we'll see that in action potentials. Let's see what I missed. Yeah, okay. So we'll move on to action potentials now. Okay, so now talking about action potentials. This is what an action potential looks like. Okay. Basically, draw it real quick. And so we have our resting membrane potential at -70. So this is the cell. And then, so there's, real quick, I'll start with this. Action potential is basically means that a neuron is firing, or any cell is firing, but in this case, a neuron. And then we also have graded potentials. And graded potentials is anything that's not an action potential, but that causes the cell to depolarize or hyperpolarize. And so you can have, real quick example, you can have graded potentials that change the change the resting membrane potential to less negative or more negative. And so you're kind of like up or down or up or down until you receive a stimulus great enough to get you to threshold. I'm gonna erase that because it looks like crap. What threshold is, and it's at approximately -55 millivolts, it's the point at which sodium voltage gated channels will open. And because the driving force is so high, when they open, they shoot sodium in super fast. And so we have this graded potential coming from a stimulus, building and building until we reach negative 55. And then the cell fires. Sodium comes rushing in. We have a peak. And then we go back down and we actually hyperpolarize and then level off at negative. That's pretty much even. Level off again at negative 70. And so what we're going to go through is a little more detail of what happens at each step. And so I'm going to mark this 1, 2, mark the threshold at 3, 4, 5, 6. We can mark this threshold at 7, hyperpolarization at 8, and then 9. So 1, we only have potassium leak channels going. We have the sodium potassium pumps creating this gradient, and we're at negative 70 degrees. We're at resting membrane potential. We can have, so at 2, it can go up or down depending on what's going on with the cell. But let's say we have a stimulus. We can have a gate. It's either a ligand gated sodium channel, I don't know exactly how to word that, or mechanically gated sodium channel. And so those will be a stimulus, and when those gates open, it causes it to become less negative. And so we'll build until you reach threshold, which then the sodium voltage gated channels will open and the cell will depolarize. And so that's 3. 4 is the depolarization. And so we still have the potassium leak channels, but the main driver is the sodium pouring in through the sodium voltage gated channels. At 5, I'm going to draw a little example of this real quick. So let's say we have a cell and we have this. I'm going to draw the gate bigger because you probably can't see from that far away. So this zoomed in, we have a gate. There's a sodium voltage gated channel, and we have this gate blocking it, and then this inactivation gate. So activation gate, inactivation gate is basically a ball that's hanging down. And so when you reach 55, this gate opens, and sodium comes rushing in. And that's right here at 4. At 5, this peak, this inactivation gate, like that, right after it depolarizes, it shoots up and blocks the gate. And so the gates are still open, but they're deactivated by this ball mechanism. And so we start to fall back down. Oh, another thing, huge. We have these potassium voltage gated channels as well. And on 4, they start to open. Well, I guess technically at 3 they start to open, but they're slower. And so they're delayed. And so by the time this shuts, so that deactivation gate shuts the gate, then the potassium gates are, the voltage gated potassium channels are open. And so that lets positive charges back out of the cell, leading to less negative. And so we start to see a fall here, or repolarization. And then at 7, yes, that happens at 6. Sodium voltage gated channels are open but deactivated, and potassium voltage gated channels are completely open, pouring potassium back into the cell. At 7, the gate's closed, the sodium voltage gated channel closes, and as well as the potassium voltage gated channels start to close. But they're slow, kind of at the beginning they were delayed, they're delayed here again. And so we actually have too much potassium come in, and we hyperpolarize, we get below negative 70. And so at 8, maybe the peak at 8, those gates finally close, and then through the sodium potassium pump and potassium leak channels, we return back to -70 or resting membrane potential. Hopefully that was a clear explanation of that. A couple things to keep in mind. I think I already mentioned this, but right here, this is depolarization. And then after 5, this is repolarization. And then you have hyperpolarization. I did mention that. A couple different things as well. We have what's called refractory periods. And so we have absolute refractory period and relative refractory period. And the absolute refractory period is this period basically between here and I think here. And so this peak, this up and down, depolarization and repolarization is absolute refractory period, which means you cannot, no matter how strong the stimulus, have another action potential in that period of time. Once we get past that and back below threshold, we have what's called a relative refractory period. And this is a period where it's like, it's resetting, it's repolarizing and hyperpolarizing and then coming back to normal. But you can still, if the stimulus is strong enough, you can have another action potential anywhere in this relative refractory period. Let's see. Graded potentials. Okay, yeah, so that's it for action potentials. And then we'll move into capacitance and length constant in an axon. Okay, so now we're going to talk about capacitance and length constant. And so the normal circular cell I drew, that was just for the sake of teaching that first part. But when we're talking about neurons, it looks a lot different. I'm a terrible drawer, but basically has a soma, these dendrites, and then a long axon. And so we need action potentials to get sent down, clear down the length of the axon. And so talking about capacitance and length constant, it's how that action potential is propagated down the axon so it can reach the axon terminal at this end and passed on through dendrites and keep the signal going. And so I'm gonna draw this a little longer. I've tried to explain this so many times. I think I have it right in my head. The wording is really hard for me to get out, so bear with me as I try to explain this. But we want to, okay, so let's start with capacitance. So capacitance is the amount of charges separated per volt. Capacitance, I think I said that right. And so a little drawing that helps me understand it. I'm gonna actually erase this. So if we have a cell membrane, pretty normal. Capacitance is basically how many charges we can get together. And so if we have lots of charges, positive charges, and lots of negative charges, this has a high capacitance. And so let me just write it over here for my own brain. So charge equals, capacitance equals charges separated per volt. And so in this, we have lots of charges separated, but we don't have a lot of separation of the charges, if that makes sense. And so the capacitance is high. What happens here is these positive charges have, like a magnet, if you're taking a magnet and pushing it against it, they want to repel. They have repulsion forces. When we have a bunch of negative charges, that that lessens these repulsive charges. And so that's why there's so much capacitance, so many charges can be put close together. Whereas if we have, so an example, we'll use myelin, and we'll talk about it more in a bit. But if we have a big separation of charge, there's less capacitance, so there's less charges. But because, so I need to describe volt a little better. Voltage is basically how bad a charge wants to cross the membrane. So in this example, they're pretty close. They want to come together, of course, but there's less potential energy here. They'll come together and hit, but here, they really badly want to come together. And so if they did come together, there's a lot more potential energy. I mean, if there is a lot more potential energy, if they came together, there'd be a lot more energy when they did come together. But so the voltage, it's increased voltage because they want to come together more. There's more potential energy. That's actually decreasing the capacitance. Where here, there's less voltage, so it increases capacitance. There's also more charges separated, and so more charges separated, so it also increases capacitance. So over here, yeah, you can see that. Increase in charges separated equals increase in capacitance, and increase in voltage decreases capacitance, and then vice versa. So hopefully that helps you understand. In the case of myelin, we have these gates, and there's lots of positive charge because in here we have a higher capacitance. Where here we don't have gates, but and because of the separation, we have less amount of charges separated, but more voltage. And so lower capacitance where there's myelin. And where there's lower capacitance, that actually helps depolarization happen faster. Something else to keep in mind, or the other big thing we'll talk about, is length constant. And length constant, right over here, that looks like an H, whatever, doesn't matter, equals the square root of Rm over Ri. So length constant is basically how far the effects of an action potential here is felt along the axon. And we have ways to increase this length constant so it'll shoot further down the membrane, and that way action potentials and depolarization will happen much faster down the axon. That's why our neurons are so fast. But so that's length constant. Rm is it's a membrane resistance. And so an example of that, so here's a good way to explain it. It's inversely proportional to permeability. And so basically, if it's very impermeable, it's a lot of, or increased membrane resistance. Sorry, I'm fumbling over my words a lot right now. And so here we have low membrane resistance, where within myelin we have high membrane resistance because it's impermeable. There's no gates along this myelin. Myelin is also, there's Schwann cells that grow lipid around this axon to insulate it, protect it, I'm pretty sure, but main purpose is to help propagate this signal down really fast. Ri is internal resistance, and so in the axon, you have these negative charges or proteins or stuff that can get away of this action potential or positive charges that will kind of cancel out this, as Shaw would describe it, bwong of energy or electrical field. But we're less concerned with that in and out of myelin. It's kind of the same. Really what affects internal resistance is the size of the cell. And so if we have a really wide and lots of space neuron or axon, you'll have high RI, or I'm sorry, you'll have low RI, low internal resistance, which is really good. But if you have really thin axon, really thin cell, then you'll have high internal resistance, which is not as good for what we want to do with this. Okay, so last thing, let's see. Okay, so we have low RM here, but high RM in the myelin. And so high RM, we'll do this. High RM is equal to increase of length constant, whereas low equals low length constant. And so we want a increased or big length constant, and so that's what this myelin does. It increases length constant. So Shaw told us that you can actually fill an action an action potential can send an electrical field to affect another gate 6 to 9 nodes down if your length constant is really high. Let's see. Yeah. So hopefully that made sense. Sorry, that one was rough. Really struggled through that one. But that's how we get signals to propagate effectively down the axon. So, last thing, in case I wasn't very clear, the purpose of myelin is to decrease capacitance and to increase length constant. So, thank you for putting up with that long video.